Greetings, world. It's such an incredible privilege to have you once again on this channel. My name is Mushabe Moses, and I'm so excited to be taking you through machine learning. And it's even more fascinating that I'm taking you through live sound tuning. Very interesting. Yeah, I'm so passionate about music and sound, and I can't wait. My name is Mushabe Moses. Let's dive straight into it. What is machine learning? It's the field of study that gives computers the ability to learn without being explicitly programmed, right? So we very well know that for a computer to solve a problem, traditionally it was meant to be given a script of rules that it would follow sequentially to solve a problem. And then machine learning comes in to take us to another strata of technology where instead of giving a computer rules to solve a problem, you instead give it data. And what it does with the data is this: it draws patterns from the data, learns from the data, and then can be able to make predictions and solve problems. That's simply it. So it draws patterns from the data, learns from the data, scrutinizes the data, and solves a problem. Then the problem we have here is sound check. Sound check is broken. Let me tell you, I'm a bass guitar man, and I must tell you that it is so stressing that you have to get at the show earlier than the rest of the people because you need to do sound check for your instrument, you know? Yeah, so you get there early, and this is what goes on. So the sound engineer goes back at the mixer and tells you to play something. As a bass guitar man, you play some slaps, and then he tunes you, right? And then he has to walk to and fro to listen to how it sounds all over the room. And it's so disturbing that he has to go to the corners and all around just to listen to how he should set the sound, right? So the sound engineer walks around the venue, listens, makes guesses, stands and repeats, doing the same thing over and over again. And being a bass guitar man, I know low frequencies disturb them a lot because they have these long wavelengths, and you know it makes them wrap around objects, and makes it difficult to tune a bass guitar in a room. Okay, for low frequency instruments. So even better, I have a solution, and that is machine learning, a learning solution, replacing the slow human feedback loop with instant data driven room analysis and collective recommendations. So, what I look at as a solution here, how about if we trained a model on sound fit for certain rooms, right? So, you go to a show in a room somewhere, and then you are able to pick up those sounds and then feed them into the algorithm and the dimensions. Of course, we have metrics, we have parameters here that we take: the room length, the resonant frequency of the room, the height. You get the point. So all of those acoustic metrics, you take them into the algorithm and the dimensions, so that instead of doing the human kind of ear tuning is reduced, and you can be able to go into a room, play a little bit of music, if you know what I'm talking about, and then microphones pick up these sounds, and from these sounds they can even calculate backwards the dimensions of the room, and then be able to give recommendations of what to change, what not to change on the mixer. You get the point? So why is it relevant? Every venue has different dimensions, that's for sure. You can't set the same sound here and there because dimensions are totally different, and it's unlikely that you will find a room with the exact dimensions as the other previous one, right? So sound settings all depend on decision made by this guy, that's for sure. It happens it often happens that after a long stretch of sound, even what they make ultimately isn't good, isn't to their perfection. So fascinating, right? So let me talk about supervised real quick and unsupervised. Supervised is where you feed labeled data into the computer. For example, let me give a literal example. A kid learns that this is a cat by either giving him pics of a cat and tell him that's a cat. That's what we call labeled data, right? So when they meet a cat, they know. And then unsupervised learning is without data. You simply without labels on the data. A data set has no labels, so you simply draw patterns from the data. So for this problem, I would go with supervised learning simply because it is straightforward and it is clear. Why? Supervised learning is one that it doesn't give categories. It gives a straightforward, and mostly for regression, it gives a value. So I want to explain this word muddiness. Muddiness, most especially for the bass guitar. Have you ever been on a show where you hear a bass guitar, but you can't really hear the articulation, the utterance of the notes? And this is it with that, with muddiness. Muddiness is you hear the bass, but you don't hear the notes. So, and it all depends on the room, because if you took that very bass and put it in a different venue, you would maybe hear the articulation of the notes, but it does not happen. So it gives you the score that it is 7 out of 0.8 according to the data it has collected in the room. Remember, it's about going into the room. The sound engineer goes into the room, plays some music, and then the system gives him this score. So he knows what to change, and it even gives recommendations of what to change. Probabilistic and deterministic model. So a probabilistic model is one in which you feed in inputs. The same inputs give different outputs. You could feed in the same inputs, so they give you outputs, but once you feed in the same inputs, they'll give you totally different outputs. That's probabilistic. And that's it about this kind of problem, because a professional bass guitar man would love a little bit of modernness, and another one would not love anything like that. So it is probabilistic that you might set this sound for a person and they might love it, and you set it for another person that may not love it. So it's probabilistic. The results change. Deterministic, it is the exact opposite of probabilistic. You give in the same results and it is always, you give in the same inputs and it is always the same results. Regression model. So I went with regression because it deals with continuous data set and the target value is numerical, right? There is nothing that lies about numbers. Numbers are real, are the thing to go. So the numbers are straightforward. They give you gives a value that's numerical and clear for predictions. The KNN algorithm. Now, the KNN finds the most similar examples to your new situation and copies it. So this is what happens. Instead of having a room, instead of having an algorithm that goes to and for looking for a solution, the KNN uses the previously learned, right? It like picks 5 of the late venues and compares it with this one, and then provides a solution according to that. And that's KNN. It's very simple. It's like giving recommendation to someone who gives you symptoms of their sickness. Because you had a friend who had the same symptoms, so you recommend the same medication. That's how KNN works. Normalization, I'll talk a bit more about this, but because of time, I'll just hint on it. So metrics and features are in different units, and so a feature that has a bigger magnitude will dominate over the others, and the algorithm will look at it as more important, but instead it is not even important. For example, this here, the room length, you see the magnitude is bigger than the rest, but reverb time, if you know sound, is more important than the room length. And so because of the magnitude, room length will seem more important to the algorithm, right? So this is why normalization matters. It brings these features to the same scale. Pruning is in decision trees. Pruning is something that is a mechanism that keeps cutting off of that tree these too specific, removes branches that memorize the training. So it prevents what we call overfitting. Overfitting is when an algorithm learns or crams. You could literally call it cramming, so that when you bring a problem, it can't solve it. You get the point? Because it has learned a specific way. When you cram, you can't go forward. So it allows for generalization. Then ensemble learning is where you combine weaker models to form a more bigger model, a more stronger model. So one of the ways of forming this is through bagging. Bagging is where you train multiple models independently and get the average. So you get a training data set, and split it and train it on different models, and then the result of each model, you get the average of the result to get a more accurate and better answer, right? And then boosting is where you train this model, does its work, fails some, and then the next model focuses on what it failed. So it is boosting, it is increasing in performance. So after a certain threshold, you are able to recognize improvement in performance, because this model doesn't anymore focus on what the other one failed. Instead, on what the other one passed. Instead, it focuses on what it failed to improve the model altogether. So SVM, which is support vector machine, is a method that draws a line between groups of things. So I would explain this in a layman understanding, which is drawing a line between the good sound and the bad sound. Once there is a clear distinction, what support vector machine comes to do, once there is a clear distinction between clear or good sound and bad sound, it is very easy to group bad sound once it comes in. You get the point? Once you go to another venue, you will be able to categorize it very fast. It is like knowing between good and bad. Therefore, once something new comes in, you know that this is either bad or good, right? So that's it about VM. Finds the line with the maximum margin. Answers the question of what is the best line, separates good bass and bad bass. Thank you very much for tuning in. Hope you enjoyed this section and this session as well. Have a blessed night. God bless you.